well, let's get started. Looks like you brought me presents. Thanks for that. All right, well, just as a couple of announcements, remember that we don't have class on Monday because this is a Tuesday, Thursday class, but you don't have any classes on Monday next week. So this homework assignment that's due on Tuesday, you won't have the opportunity to consult with me on Monday before that's due. Now, I don't ordinarily have office hours on Monday, but if my office door is open and you've tried on a problem, come see me even if it's outside of office hours. I'm happy to help you if I can. Since you won't have that opportunity for this class, you can send me an email if you come into any trouble as you're working on the assignment over the weekend. But I think after some of the things we take a look at today, you should be able to get through that homework assignment without too much trouble. So any questions about the announcements or things that we covered in class last time? Any questions? All right. We're going to continue talking about fluid properties today, and we'll start off by discussing the principle of elasticity and volume change of fluids. Now, in the last class, I talked about how we generally assume that water is incompressible, and that's one of the main distinguishing characteristics between a liquid and a gas is that gases are compressible and liquids are incompressible. But liquids, the reality is, are a little bit compressible under very, very high pressures. And the bulk modulus of elasticity is a fluid property that allows you to classify how compressible a liquid actually is. And so it's a fluid property that you can look up in the book, and we'll do that in just a minute for water. We'll look up the bulk modulus of elasticity, and in your homework assignment it asks you to compare a couple of different fluids and their bulk modulus of elasticity. But the formula that's shown there is dP, which means a change in pressure relative to a fractional change in volume. And so dV divided by V. And this V with a cross through it, that's sometimes used to indicate volume because there's actually a lot of different V's in fluid mechanics. There's velocity is a main one, and volume. And so the V with a cross through it you can usually interpret to mean volume. So in this case, fractional change in volume, if you think about there was 1 liter of water, and then how much of that, if you're applying a pressure to a liter of water trying to get it to compress, if the change in volume was 10% of the original quantity, then dV would be 0.1 divided by 1 liter. So that's how you use the dV relative to V. The fractional change in volume is talking about relative to the original quantity of water that was available, or any liquid, how much changed when a certain pressure was applied. And then the reason why there's a negative sign there in the definition of the bulk modulus of elasticity, that negative sign means that when you apply a positive pressure, then the volume decreases. And so there's an inverse relationship between applying a pressure and the volume occupied by the fluid. Another way of thinking about it, the bulk modulus of elasticity for water, 2.2 times 10 to the 9th pascals. And we'll talk about the magnitude of that in just a minute, but I want to introduce this other way of thinking about it. You could also think about the bulk modulus of elasticity as the negative of delta P divided by V divided by the delta V. And so that's really the same as what was already there, right? It's just using delta instead of the D. So this is the same. But the other way of thinking about it is in terms of density. And so when you compress a fluid, you're actually changing its density. When you're compressing a liquid, you're going to take the same mass of H2O, and it's going to be occupying less space. And so you could, instead of thinking about it as a change in volume, you could think about it as a change in density, because you'll have the same mass and a different volume occupied by that mass. All right. So 2.2 times 10 to the 9th pascals. When we have unfamiliar units like pascals, sometimes that kind of a number doesn't really mean anything to us. And so just to get a sense for that, 2.2 times 10 to the 9th pascals, what is atmospheric pressure in pascals? Does anybody know atmospheric pressure in pascals? It's maybe something, remember STP from chemistry, standard temperature and pressure?
760.
760 is pretty close. It's 760 millimeters of mercury. And so that is one SI way of measuring atmospheric pressure. In terms of pascals, it's 101,325 pascals. That is standard pressure, meaning the average atmospheric pressure at sea level. You know, atmospheric pressure varies from day to day. On a stormy day, they usually have lower atmospheric pressure than a high pressure front is usually a sunny day, but on average at sea level, atmospheric pressure is 101,325 pascals. And so that is 0.1 megapascals. 0.1 megapascals. What this bulk modulus of elasticity is 2.2 gigapascals. And so you know the difference between a megabyte and a gigabyte. And so it's 1,000 times different. And so the bulk modulus of elasticity means that in order to compress water any meaningful amount, you're going to have to apply a really, really high pressure. And we'll take a look at that in an example here in just 1 second. Literally 1 second. All right. We've got 5 gallons of water. It's open to the atmosphere. And what if we apply a pressure of 5 megapascals? And so we've actually got a mixed units problem here. Part of the problem is in traditional units. Part of the problem is in SI units. So 5 gallons of water open to the atmosphere, and then we apply an additional 5 megapascals. So what will be its new volume after that change in pressure? So you've got the bulk modulus of elasticity for water. We know what the delta P is going to be, and we know the original volume of the water. Solve for the change in volume, and then apply that change in volume to the original volume to find the final volume. All right? You can, of course, in any of these examples, work with the people sitting next to you. I don't expect it to be silent in here. We're not in a monastery. We're learning fluid mechanics, so that's like sort of like being at a concert, you know, kind of like a really happy, joyous occasion when you're in fluid mechanics. So feel free to talk amongst yourselves. Were there any extra copies of the notes? Everybody get one? I put the grades online for your in-class exercise from last time. I'll hand these back. All right, so 5 gallons of water is equal to 18.925 liters if we convert that from traditional units into metric. We can rearrange the definition of bulk modulus of elasticity to find the delta V, and then simply substitute in each of the variables. We've got the change in pressure that's being applied of 5 megapascals, and by the way, a pascal is a Newton per meter squared. And so it's a unit of pressure. And pressure is force over area. So a Newton of force expressed over 1 meter of surface area And so instead of writing 5 megapascals, I wrote it so that the units would cancel out in a really clear visual way. 5 million newtons per meter squared, multiplied by the 18.925 liters, divided by 2.2 times 10 to the 9th newtons per square meter. And we end up with that the change in volume is negative 0.0430 liters. So think about it. If atmospheric pressure is 0.1 megapascals, and here you're applying 5 megapascals, and so that's essentially 50 times atmospheric pressure. All it's changing is 0.04 liters out of 18 liters. And so that's a very small fraction of the original volume, even though we're applying an incredible amount of pressure. And that's kind of why liquids are generally held to be incompressible, is because, well, yes, they can be compressed, but not by very much. So we get the final volume 18.882 liters. All right. You'll notice through the semester that I'll never write an example on the board without writing the units in every single step of every problem that I work through the entire semester. And I do that because I'm trying to set a good example for you. I think that you should do the same thing. Always write the units in every step of every problem you do, whether it's just some little back of the notes calculation that you're doing just to try and remind yourself of something, or if it's in an exam. Even if you're in a hurry in an exam, you should still write the units because it's an investment in catching mistakes. And you know, what if I had left this volume in gallons? Well, it's really obvious if you're writing the units down that it shouldn't be in gallons. Like if I had, you know, as I'm writing all the units, if I wrote 5 gallons, well then it's obvious that there's a discontinuity there. But if I don't take the time to write any of the units, it's less obvious that there's a problem if I am just putting numbers in. If I just write 5 million and 5 and 2.2 times 10 to the 9th, sure, you know, you can multiply those numbers together, no problem. But you shouldn't multiply those numbers together, and it's only obvious when you continue to write the units. And so what I'd encourage you to do is always write the units in every step of every problem you work. All right? Any questions about that example? Okay, what are we looking at here in this photo?
Honey.
Sweet, sweet honey. Yeah, that's right. Over the summer, I actually got a beehive at my house, and so I've been eating a lot more honey than usual. And I only got stung one time so far, so it's working out great. But, so if this is honey and that's a spoon, what are these? Air bubbles. Why are we seeing those air bubbles? So, you know, like if that was a spoon pouring out water, I don't think we'd see air bubbles quite like that. Why are we seeing them in this photo? And I'll let you know, this isn't like any special high-speed photography. It's not like this was an exposure duration of 1/1,000,000th of a second. I mean, this was just a standard picture here. What are those air bubbles from? Okay, absolutely. The liquid is moving much slower than water if you poured it out of a spoon. So the reason why you can see the bubbles is that the bubbles have kind of a harder time escaping the liquid than they would if it was water. So let's watch a video that sort of touches on that, and we'll discuss it a bit further. No VLC, huh? What about Internet Explorer? Maybe. Two equal sized containers of liquid. They're both at the same temperature. They're both clear, and in fact, both of these liquids have the same density. So they appear to be very much alike. And so unknown hand on screens, picking it up, shaking it. This is water, liquid shakes. There appears to be a difference there with the liquid on the right. Okay, pouring the water. You can see how it responds to the pouring motion. Okay. So what's going on there? What is this fluid property that causes that liquid to pour so slowly? It's a refreshing glass of glycerin. You wouldn't want to chug a glass of glycerin. That's what that liquid was. And so, what's going on there in that picture? Any thoughts on this fluid property that causes liquids to pour slowly? What it's called? Viscosity. I hear some muttering. Muttering's fine. Yeah, it's viscosity. That's the fluid property. And viscosity we can understand in terms of strain, the definition of strain. So you'll remember from previous classes that strain is a physical body deforming under the action of applied forces. So I've got a metal ruler here, and let's watch this metal ruler strain. If you press on it at both ends, so I'm applying a force, then the physical body deforms. Now, one of the differences between a solid and a liquid is that a solid stops deforming, but a liquid keeps deforming as you apply forces. And so I'll apply forces and it'll reach some equilibrium point and it stops deforming. I'm applying the same force. For it to deform more, I have to press harder. I have to apply a greater force. But eventually, it reaches an equilibrium that a liquid won't. I'm going to pass this around so you can all have the experience of deforming a physical body. This is like a kinesthetic learning opportunity here. So a solid ceases to deform when equilibrium is reached. And that proportionality between how hard are you pressing and how much did it deform, that's the shear modulus. And so this is a steel ruler. If it was a titanium ruler, for the same force, it would deform less because titanium's a really rigid, strong metal that would have a larger shear modulus. So the analogy we're going to draw is that what we've just talked about is the response of a physical body under the action of applied forces for a solid. A liquid has an analogous response. Now, in the case of a liquid, there is something, a proportionality factor between how hard do you press and how much does it deform. Remember, we're saying steel versus titanium is steel deforms a lot, titanium wouldn't. Well, think about that liquid in the beaker that was being shaked. One of those liquids, they're applying the same force, the force of shaking it back and forth, the force of tipping the container, but those two liquids were behaving differently because they have a different proportionality factor in the relationship between the applied force and the deformation. And so a liquid continues to deform as long... You didn't bend it. We're enemies now. No, that's all right. We're not enemies. But I bet everybody else bends it. Yeah. All right. So the liquid, if a propeller is turning, the propeller on a boat, as long as it turns, water is going to be deforming around that propeller. It doesn't reach the same equilibrium that a solid does as you press on it. Now, that proportionality factor in the case of a solid is called the shear modulus. Well, the analogous proportionality factor in liquid is called viscosity. Now, there's three names for the same thing: dynamic viscosity, absolute viscosity, or just plain viscosity. Those three phrases mean the same thing. They have the same units. We're talking about the proportionality between an applied force and the physical deformation of the liquid. All right. Let's watch another video clip. This one I think is formatted appropriately so we won't have any trouble. And then we'll talk about that slide there. All right, in this video, they don't give you a lot of context, do they? You remember when we were in the lab and we saw the flume? The flume is that rectangular channel that water starts at one end and it flows downstream. This is a close-up of a flume. You don't see upstream the water is coming from this direction and it's going that way. That is a straw. So somebody's putting a straw down into a flume and water is flowing from right to left. Okay, so let's see what happens with this straw. This is riveting TV here. Okay, the straw's at the bottom of the flume, injecting a dye, a green dye. You can see that the water's moving. How do you know that water's moving? You just know it when you see it, right? Those are called streamlines, and we're going to talk more about streamlines when we get into chapter 4. But what we're seeing right now is streamlines. Now, there's kind of a funny thing though. At the bottom of the flume, the water, the dye that gets washed away is in the channel. But the dye that is very, very close to the bottom of the flume, it persists. It's not going. Now, that dye has been down there, like the straw was down at the bottom for only a second. So the straw's at the bottom, inject the dye. All right, so there's some dye down there, but it's not being washed downstream. And even when they stop injecting the tracer, or the dye, out of the straw, it's still there. Okay, they're stopping the injection, so this is the last of it. This is the last of the dye. It's flowing away. Why is that still down there? What's going on at the bottom of the flume? This isn't sticky. It's not like the dye itself is a glue. That's not the answer. What do you think's going on? Well, what's moving the dye?
Water.
Flowing water, velocity. You know, velocity moves things. Things move when they have velocity. This isn't moving, so what does it lack? It's not moving because it lacks velocity. So down there at the bottom of the channel, the water doesn't have any velocity, but when he moves the spoon around, that's forcing a velocity at the bottom of the channel. So what we're talking about in this next slide, come on, it's called the no-slip condition, and it's an effect of viscosity. When fluids resist movement, then at the bottom of the channel, where the water is in contact with the channel, here in this diagram, water's moving to the right in this case. In the last one we looked at, it was moving to the left. Now what's this? This blue line is a velocity profile. And what that blue line says is that the further away you get from the bottom of the channel, the velocity is increasing. And this makes sense because it's the channel that is imparting resistance to flow. It's kind of like friction. You know, moving water is resisted by the surface that is holding stationary. And so the water that's further away from that frictional surface is moving at a higher velocity. But if you get close to the frictional surface, then the velocity is very small. So, you know, this vertical line, how far the blue line is from this vertical line is what's representing the velocity of the liquid. So when you're high up off of the bottom of the channel, up here, there's a big velocity because you're far from the friction surface. Now at the very bottom, the reason why this is called the no-slip condition is it's not like water can slip over a surface. There is a gradual transition of the water that's right next to the solid has the same velocity as the solid. At the interface of the liquid and the channel surface, there's the same velocity. And so viscosity is causing this velocity profile. So we think about this in terms of resistance to flow. In terms of the variables that are shown, the V means fluid velocity, Y is the distance vertically from the solid surface. And so if we consider the dV dy, we call that rate of strain. how quickly the velocity is changing with respect to distance away from the channel boundary. And so down here, the rate of strain is great because the velocity is increasing a lot with some small marginal increase in elevation. But then once we get up here, the velocity is not increasing as much. So the rate of strain is greatest right at the interface of the liquid and the solid. And then once you get far away from that no-slip boundary, then its effects aren't really felt in the same way as when you're very close. Okay, mu, Greek symbol mu, is the variable that we use to represent viscosity, also known as dynamic viscosity, also known as absolute viscosity. And it has units of Newton seconds per meter squared. So shear stress is an applied force per unit area. So shear stress is going to have units of newtons per square meter. And it's applying the shear stress that causes the deformation or the change in the substance that's having the force applied to it. And so shear stress, the definition of shear stress is the rate of strain dV dy multiplied by the viscosity. That's how remember we called viscosity a proportionality factor earlier. In the analogy between the solid and the liquid, there was the shear modulus for a solid, and for a liquid there was viscosity. It's what relates two different things. Viscosity relates how much shear stress is applied and how much the liquid deforms. This dV dy term is basically a quantification of how much the liquid is deforming. So that what would you think of a channel where the velocity profile looked like this? This is case number 1, and this is case number 2. And this has the same units here. This is going to be velocity, and this is distance from here. So this is y. So how are case 1 and case 2 different? If it's the same channel and the same liquid, what's going on in 1 versus 2? It's got more velocity. It's the same fluid, it's just that maybe we turned up the pump. The water's moving more quickly. And so there's more of a response. In situation 2, what we're seeing is that there's a bigger dV dy. So we must be applying more shear stress. And so case 2, it's more deformation because more shear stress applied. If these are both the same liquid. So we could do that in the flume by increasing the slope, by making it steeper. If we make it steeper, we're applying more of a shear stress to the liquid. And so the proportionality factor, what describes how much a liquid deforms relative to the shear stress that's applied, that's the viscosity. That's that factor that characterizes how thick something is. We think of it in terms of thickness, when really it's not related to density. Sometimes we think viscosity and density are related, but they aren't. Not necessarily. Okay. So let's consider this conceptually. Is it easier to walk through air or water? If you're in a swimming pool and you're walking, can you walk as fast as you can when you're walking through air? Why is it that you walk slowly in a pool? Why can't you walk faster in a swimming pool? Have you ever thought about that?
Water has more viscosity than air does.
Okay.
More dance.
That's true as well. Water is more dense than air is. And so think about, like, what's in the way of your leg? When you walk through air, something's in your way. Like, it's not like there is nothing in front of me right now. There's air in front of me. When I walk across a room, air is deforming around my body. As I walk through the air, it gets out of the way. But when you walk through water, the water resists the movement. It has a greater viscosity, and so it has less deformation for the same shear stress that's applied. And so when I'm walking 1 foot per second through air, the air deforms easily because it has low viscosity. But when you walk 1 foot per second through water, that proportionality factor dictates that there is going to be, for the same shear stress applied, since water has a greater viscosity, there's going to be less dV. There's going to be less of a change in velocity as it gets out of your way. And so that's part of why it's more difficult to walk through water than to walk through air. So why is it easier to walk through air? It's because you can think of it in terms of friction. There's less resistance to movement through the air. And it goes back to the definition of the rate of deformation. Air deforms out of your way more quickly when you apply the same shear stress than does water. Water moves more slowly. If you have a box fan, you've seen the box fans. I think you probably did the wind turbine project. Remember that from Engineering 107? Never done that before, have you, Andrew? So those big box fans, what if you put that box fan down into water? As big as those fan blades are, it probably wouldn't even be able to spin. If it did, it would spin very slowly because the air deforms more easily. If you compare an air fan to a water impeller, they're shaped very, very differently. On a boat, it's kind of incredible how small a propeller is on a boat compared to an airboat. If you've ever seen, like gator hunters or something, whatever, on National Geographic, the fans they have up on those are enormous. They have a span of 1 meter or 2 meters. They're very large because they need a greater surface area because air is deforming more easily than water does. And so that accounts for the size and the different sizes in the propeller is the viscosity of the fluid. Okay, so we've previously said that shear stress is viscosity times the rate of strain. Rate of strain. Strain is a response to stress. The response to stress in this liquid is the change in the velocity profile. Okay, so here is a graphical illustration of viscosity. Air deforms a lot. Lots of deformation for a little bit of shear stress applied. I don't have to apply very much shear stress to get the air to deform out of the way when I walk. Water, on the other hand, has less deformation for the same shear stress applied. Oil has an even greater viscosity, meaning that it does not deform as much for the same shear stress that's applied. And so the slope of these lines, the slope of shear stress relative to rate of strain, that is viscosity. So all we've done here is just rearranged that equation for mu. So we can think of viscosity in conceptual terms. You have a context in the world, you know what it's like to interact with different fluids, and that helps you to understand, sort of have an innate instinct for what viscosity is. But then you can also understand it in graphical terms, just the ratio of deformation to shear stress. So you can think of viscosity as the slope of the line or the ratio between shear stress and the rate of deformation. It's a proportionality factor. Now, I already said that there's 3 names for viscosity. There's absolute viscosity, dynamic viscosity, and then just viscosity by itself. And all 3 of those things have the same variable mu. They mean the same thing. Kinematic viscosity is a little bit different. And what kinematic viscosity does is it takes into account the density of a fluid. A lot of equations that we use through this semester in fluid mechanics have both viscosity and density in the equation. And so what kinematic viscosity does is it takes both of those things into account. It's a way of normalizing the viscosity of a fluid relative to its density. And so we can combine those two factors together in terms of kinematic viscosity. And so kinematic viscosity is the ratio of absolute viscosity to fluid density. So if you divide the viscosity of a fluid by its density, that's the kinematic viscosity. And it has units of meters squared per second, length squared per time. So remember that viscosity is Newton seconds per meter squared, and kilograms per cubic meter. All of that cancels out to meters squared per second if you take into account that a Newton is a kilogram meter per second squared. And so air and water have very different viscosities, but they also have very different densities. And so kinematic viscosity is a way of trying to compare apples to apples, so to speak. You know, if you have two fluids and they have radically different viscosities, part of that difference in viscosity might be due to their difference in density, and that kinematic viscosity takes it into account. So these are the four words, the four phrases that you may hear occasionally. If it just is viscosity, it's talking about mu, absolute viscosity, mu, dynamic viscosity, mu. It's only when they specifically say kinematic viscosity that you need to take both the viscosity and the density into account. Do you remember what the density of water is in terms of kilograms per cubic meter? How many kilograms are there in a cubic meter of water? 1,000. So the density of water is 1,000 kilograms per cubic meter. One thing that's easy to remember, that the typical kinematic viscosity for water is 1 times 10 to the minus 6th meters squared per second. And the typical viscosity of water, therefore, because we know that viscosity is density times kinematic viscosity. So if I multiply this by 1,000, it's 1 times 10 to the minus 3 Newton seconds per meter squared. So these are just sort of typical values for the viscosity. Viscosity varies as a function of temperature, though, and you know that. Anybody who's changed their oil before knows that. If you want the oil pan to empty quickly, you heat up your engine first. And then when the oil is hot, it flows a lot more quickly because it has lower viscosity. It's a little bit confusing sometimes. When we talk about a high viscosity, that means lots of resistance to flow movement. And so there's more resistance to the shear stress that's applied. Low viscosity means it's a very thin or runny fluid. Now, we apply viscosity concepts in order to find the shear force required to overcome viscosity. So remember that the units of shear stress has units of newtons per meter squared. And so if you multiply a shear stress by an area, as is indicated on the board there, then you'll just get units of force, newtons. So if shear stress is newtons per meter squared and area is meters squared, then shear stress times area has units of force. So how does that work? It's basically just the viscosity times area times du dy. Now, in fluid mechanics and physics, oftentimes u is meant to mean velocity in the x direction. And so here where it says du dy, that means exactly the same thing that it did in previous slides when it was saying dv dy. And the book sort of switches back and forth between them, and I wanted to mention it explicitly in class just now so that you don't get thrown off by that and wonder, well, what are they talking about with u? That just means velocity, same as it was previously. So here we've got the rate of strain, du dy, remember, is the rate of strain, area, and viscosity. So you can find out the force required. You have to apply a force to overcome a viscosity. And we've got an example here in just a minute that sort of makes that concept physical. But I wanted to show you the units development of how you get force in terms of newtons, where the shear stress would be okay, so viscosity newton seconds per meter squared, area meter squared, and du, so that's a velocity, meters per second, and a dy is a distance, meters. So that all works out to newtons if you cancel out the units. So du dy is in a lot of the problems we solve, we'll assume a linear rate of change, and so du dy will often we'll substitute in a velocity and an incremental distance and assume that there's a linear change in between 2 points. So if you assume a linear velocity distribution between 2 points. So here's a physical example that hopefully can make these equations make sense. So let's say we've got a tank of glycerin, and remember, glycerin is that liquid, it was the liquid on the right in the video that we watched. It was that very viscous liquid that when the hand went to pour it, it sort of came out and it looked like cake batter, right? That's what I sort of thought of as he was pouring it. As I was like, man, I'm so hungry for a glycerin cake right now. It looked like it was spreading out. All right, so this is a tank full of glycerin, which we know is a really viscous fluid. And here we have a metal plate. It's got an area of 3 meters by 2 meters. So 3 meters long, 2 meters into the page. It's got a top and a bottom. You know, planes have those, both a top surface and a bottom surface. And so it's in contact with the glycerin on the top and the bottom. And the no-slip condition, remember, says that any place there's contact between a surface and a liquid, there's going to be resistance. And so if we tried to pull this, we're going to apply a force to pull this liquid through the glycerin, there's going to be resistance to motion. If we try and pull that plate through the liquid is going to resist it by pushing that way on the plate. So, you know, we pull this way, the liquid pushes that way to resist the movement. Now, the distance is given as 1.2 meters from the top of the plate up to the tank there, and 2.4 meters from here down to the bottom. Now, it actually matters how far it is from one solid surface to the other. And you understand that most easily when you take it to the extreme. If you think about a car engine, for example, that has very, very tight tolerances where the piston fits into the cylinder very closely. You know, in a car engine, they've got these cylinders. Boy, I really can't draw. It's a good thing computers came around. All right, so there's a very small gap there. Very, very small gap. It would be harder to force that piston up if there's a small gap than if there's a big gap. And so having a big gap, you just sort of can intuitively know it's going to be easier, you know, if you've got oil lubricating the gap space between the piston and the cylinder, as you usually do in a car engine. If you've got a big gap, then the piston will move more easily than if it's a really small gap. That same principle is in effect here, that the 2.4 meters that's below the plate is going to cause less resistance to movement than the interaction between the plate and the liquid and the other solid surface above the liquid related to that 1.2 meters. So in this example, we're going to want to try and pull that at a velocity of 0.58 meters per second. So we have a velocity defined. We know the viscosity of glycerin. We know the area of the plate. and we know the gap distance. And so think about the information that's given in the equations above that thick black line, and I'd like you to try and calculate what's the force required in order to cause that motion. What time do we get out of class? 11? 12:15? Okay, we got plenty of time, right? All right. This is going to really take some getting used to. All right, so go ahead, talk amongst yourselves, try and calculate what's the force required to move that plate at 0.58 meters per second. So this plate has a top and a bottom, and there's a different amount of force required to overcome the viscous resistance on the top surface versus the bottom surface. Since the plate is closer to the top of the tank, that's going to require the greater amount of force. There's going to be the greater resistance to moving it at a velocity of 0.58 meters per second when the gap is 1.2 meters than when the gap is 2.4 meters. So we can calculate the total force. And this is when it reaches equilibrium. Now, of course, there's going to be a different amount of force to start it moving. You know, when it's motionless and you begin the movement, that's going to be one thing. This is talking about to keep it moving at a velocity of 0.58 meters per second when it has reached equilibrium. So this is one application of viscosity, is trying to calculate the forces required to cause some sort of a deformation of the fluid. In this class, we sometimes have pop quizzes, and sometimes it'll just be to check up on your comprehension of concepts, and we'll probably have a pop quiz on Tuesday. Not much of a pop quiz when I tell you it's probably coming, but you'll come to sort of like feel it in your bones, you know, like old-timey people in their knees, they're like, oh, it feels stormy. You'll start to feel, it feels like a quiz is brewing. And oftentimes they brew right after homework assignments are due. Any questions about the example? A few other things to say about viscosity is that viscous resistance is independent of the pressure. So pressure doesn't change the viscosity. You know, the viscosity of water is the same at the bottom of the ocean as it is at the top of the ocean. Just the fact that you're lower or under a greater column of water, that doesn't change the viscosity of the fluid. And what causes viscosity? Well, it has to do with the molecules inside the liquid and how tightly bound they are to each other. And because of that, because it's down at the molecular level that viscosity arises because of intermolecular forces, liquid and gases have a different response to changing temperatures. Now, we've already talked a little bit about how hot oil has less viscosity. It becomes more runny as the temperature increases. Well, as it turns out, gases actually have the opposite effect. Gases become more viscous as the temperature increases. And here's an illustration of that effect. One thing to point out is that this is a logarithmic scale on the y-axis, and this is kinematic viscosity of both air and crude oil, comparing those two. And so what we would expect, the typical behavior of hot oil, as you increase the temperature, the viscosity decreases, meaning that it's going to deform more easily under an applied shear stress. But the air, as the temperature increases, so does the viscosity. And the way to interpret and understand that is that, remember, in air, the molecules are moving around, and as the temperature increases, the molecules are moving around, they have greater activity, and that greater activity and increased collisions actually increases the viscosity of the fluid. Whereas in the case of liquids like oil, the increased temperature decreases the viscosity because those molecules are becoming less tightly bound to one another and more able to move about freely. So I guess there's sort of a threshold at which the movement, the kinetics of the molecules starts to inhibit the movement of an object through that fluid. So, another difference between gases and liquids. Both are fluids, but gases and liquids have a different response to the change in temperature. Another really interesting thing that has to do with viscosity, and this may be my favorite thing as it relates to viscosity, is the difference between a Newtonian fluid and a non-Newtonian fluid. And to illustrate, let me show you video clip number 4. Where's video clip number 4? Well, shoot. Hold on just one second. I bet I can find it. A Newtonian fluid is one where, like water is a Newtonian fluid, the viscosity doesn't change in response to the shear stress. But there are some non-Newtonian fluids that are considered shear thickening, and a shear thickening was the cornstarch water mixture that we just watched. And so in a shear thickening fluid, the viscosity gets larger with the shear stress that's applied. A shear thinning fluid, ketchup is an example of a shear thinning fluid. And you know, when people are shaking a bottle of ketchup, if it's a glass bottle and trying to get the ketchup out, well, when you shake it like that, part of the reason you're able to get it out is that you're applying a force to the liquid towards the orifice inside of the bottle. But another thing is, as you shake it, you're actually reducing the viscosity of the tomato ketchup. And so shear thinning fluids are those which have a reduced, remember that the slope of these lines is the viscosity. So in this case, the slope is increasing with the shear stress that's applied, so that's why it's a shear thickening fluid, whereas a shear thinning fluid, as you have a greater shear stress that's applied, the viscosity or the slope of that line is decreasing. So that's kind of an interesting little asterisk next to viscosity, is that not all fluids have a constant viscosity. Questions like this: what is the viscosity of water at 80? How does the viscosity change from 50 to 100? In your textbook, there is a table of fluid properties as a function of temperature, and I think I remember that we looked through that last time in class. And one of the columns in that table is dynamic viscosity, and you'll notice it is what has the units of Newton seconds per meter squared. And the other column is kinematic viscosity. And so the kinematic viscosity is simply the absolute viscosity divided by the density. The text has all sorts of tables of viscosity, a lot more information for air and water than other liquids. Like, it doesn't have all the different temperatures for glycerin or all the different temperatures for mercury, but you can still find the dynamic and kinematic viscosity for those. And a chart of showing change in viscosity as a function of temperature. There's lots of information in the tables is the point. All right, we're going to finish off with just a very briefly touching on the ideal gas law. And you probably remember from chemistry, PV equals nRT. And the ideal gas law relates the number of molecules that are present to the volume that's going to be occupied by that number of molecules at a certain temperature and pressure. And the universal gas constant, which has a variety of different values depending on the units that you're using, is what relates the number of molecules to the pressure, volume, and temperature that's occupied. Now we can rearrange the ideal gas law, and if we isolate the pressure term and then substitute in the molecular weight of a gas in both the numerator and the denominator. One thing to keep in mind is that if you have the number of molecules and number of moles multiplied by the molecular weight divided by the volume. So that is mass per unit volume. That's density. And the definition of the universal R value, if you divide that by the molecular weight of the gas, each individual gas has its own gas constant R. We can rearrange that to find the density of a fluid as a function of pressure, the R value of that fluid, and the temperature in Kelvin. So you have a homework problem that asks you to calculate the density of a fluid. You can calculate the density, I think it's a gas, you can calculate the density by knowing the pressure that that gas is at, the temperature of the gas, and then looking up out of the tables the R value for whatever that gas is. And to illustrate that point, consider this example of we've got some room with dimensions of 4 by 5 by 6 meters, and inside the room the pressure is 100 kilopascals and the temperature of the air is 25 degrees Celsius. And so in this example, what we're going to do is go through the process of finding what is the density of the air, and then remind ourselves the definition of specific gravity. SG, or specific gravity, is something that we talked about very briefly in class last time. And so we'll apply that to calculate the specific gravity of that air, and then also, knowing the volume of the room, calculate the mass of air. All right. So in this gas law example, we need the R value of the gas. We're going to need the R value. And if you just like were to try and look up what is the R value for air, there's tons of different values depending on what units that you want it in. And in this case, the units that we want are going to be 287 joules per kilogram Kelvin. And we're going to substitute it into this equation, and we'll come back to these units, and I'll show you how they work out after we do that. The pressure of the air that's defined in the problem, 100 kilopascals, so 100 kPa is the same as 100,000 newtons per meter squared. That's the pressure. For a temperature of 25 degrees Celsius, that's 273 plus 25 equals 298 Kelvin. And so the density of the air is going to be the pressure divided by R times T. So 100,000. Now a Newton per square meter is the same thing as a 100,000 kilograms per second squared times meter, if you consider that a Newton is a kilogram meter per second squared. That's what this works out to. A joule, if you were to break down what a joule is and find the absolute base units of what this is, it is 287 meters squared per second squared Kelvin. If you consider the joule is a Newton, let's see, joule is a Newton meter, and a Newton is a kilogram meter per second squared. So the way that this is all going to work out is that we have the pressure is 100,000 kilogram per second squared times meter. The R value is 287 meters squared per second squared times Kelvin, and then the temperature is 298 Kelvin. So that works out to a density of 1.169 kilograms per cubic meter. And I think that little noise means that class is over. We'll pick up the last part of this example when we get together on Tuesday, calculating the specific gravity in the room and also the mass of air in the room.
On that question,
Excuse me?
the homework question that involved this.
I don't think so. But if it does, I bet you could figure it out.
Well, I was wondering if the absolute, talks about the absolute
What?
pressure.
Okay. Yeah, the absolute pressure is what you'd substitute in there. Let's just take one final look at the announcements. The homework assignment is due on Tuesday. Like I mentioned before, as you're working through it, if you come into any problems that you can't figure it out, feel free to send me an email since we're going to have a holiday on Monday.